Very seamless. Oh, there we go. Now the microphone's working. Good morning. So we want to have so we're going to start in a few minutes with the Diamond Sponsor Key presentation. We do want to have a fairly seamless transition from that talk to the spotlights. So I'd like to ask at least the first 5 papers for the Spotlight 2 to sort of stay over here maybe for the first presentation, just so that we're quick to set up for the spotlights. All right, thank you.
Welcome to the first sponsor session, and my name is Jay. I'm the sponsor chair for CoRL this year. And today it's a great pleasure to have Mustafa Mukadam with us. He is a staff research scientist at FAIR, where he leads the manipulation and tactile sensing team. And prior to joining FAIR, he received PhD in robotics from Georgia Tech. His research spanned robot planning, robot perception, and many, many other fields. His work has been recognized as a 2018 IJRR Paper of the Year award. Without further ado, please take away.
Thanks, Jay. Hello, everyone. Good morning. So today I'm going to talk about robotics and touch perception research we're conducting at Meta Fair. So you might ask, why is Meta doing robotics? So I thought I would give like a primer for that first. Uh, so all the robotics folks are part of the FAIR organization, and their mission is to advance AI research. And so the argument is essentially interaction with the physical world is a key step in making progress in AI, and that's why it makes sense to have robotics research conducted at FAIR. And then the sort of other parallel reasons in terms of kind of Meta's priorities are, in today's land, generative AI and AI agents, which sort of connects to all the work we do in robotics in planning and reasoning, and then also the kind of other priorities in across Meta on AR and VR applications also connects to egocentric perception and hand-object interactions, that sort of stuff. So that sort of cumulatively justifies kind of why we would want to do robotics research at Meta. So I'll give a brief overview of kind of the different buckets of research we are conducting, and then I'll dive a lot deeper into some of the work my team is specifically working on. So I put all of this across a grid, as someone does, just to kind of lay out the land of what's going on. So on the y-axis, you see sort of high, mid-level, low-level skills. You can think of those in terms of the horizon of decision-making. And on the x-axis, you can kind of go from like navigation to mobile manipulation all the way to just kind of hands and dexterity. So the first bucket is sort of in the high-level navigation / mobile manipulation land. We had a recent release called Partner. It was a huge team effort, all of these folks involved in that project. And the idea was to build a kind of first-of-its-kind benchmark that sort of put humans and robots together in a household environment to coordinate on tasks and study sort of human-robot interaction, and sort of make these types of problems and evaluations for them easy. So it's kind of a really large kind of evaluation data set of almost 100,000 natural language tasks across many diverse simulated scenes and many objects. And it's all built on top of Habitat 3 simulator. The next bucket is sort of in the middle with sort of navigation and manipulation skills. And one of the projects a large part of the team focused on was OpenEQA, which is sort of a new incarnation of the classical visual question answering formulation, where in this setting, it's in an embodied form. So if you ask a robot, so for instance, a question, the robot can kind of move around, go and look for something and answer those questions. Like, where did I leave my keys, for example? And it would sort of go around the room and look for it. And this also kind of provides this large evaluation data set across many different tasks, I think almost 1,600 tasks. All right, so the next piece I want to kind of jump a lot more deeper into is all the work we're doing on the dexterity axis. So before I jump into that, I wanted to upfront acknowledge kind of all the members of the team involved. It's a huge team effort across many different researchers, engineers, and even past members from our team and external collaborators. And all of this work would not be possible without this huge team effort. So why do dexterity? I think this audience probably doesn't need that much motivation, but I'll give one anyways. Today's AI landscape is quite interesting. We have kind of really advanced cognition capabilities with LLMs, and they can clear bar exams, but we barely have robots that can kind of even match toddler level capability in manipulation. We're still sort of primarily focused on pick place type things. And kind of the key bet our team was making was tactile sensing is essentially the key missing ingredient that has prevented us as a community from making really a lot of progress in dexterity. So that's kind of the main axis of focus or thrust we had in our group. Just a quick primer for those uninitiated on tactile sensors. One of the kinds of tactile sensors that's quite kind of prominent these days, just because of the easy access and affordable cost, are these class of vision-based tactile sensors. One of them called Digit, which was actually developed at Meta. And you can see sort of this exploded view, which gives you an idea of what that sensor looks like. It's essentially a gel in front of a camera and illuminated inside through LEDs. So as you touch something, the gel deforms and it's captured by a camera. And so essentially you're kind of converting touch signals into kind of a video stream. Of course, these images don't look anything like real images, so it still opens up a lot of interesting kind of perception questions. So the video on the right you see is sort of what the raw output of the sensor is. And this work was led by Mike Lambetta, who is around, and you should talk to him offline more about the sensors. So I'll give a quick overview of kind of what this journey looked like for us since the sensor came out back in 2019, 2020. We sort of slowly started ramping up into how to actually use these sensors in manipulation, how to study perception for them. And kind of we learned some interesting lessons along the way. As naturally anyone would start in manipulation, we started just pushing objects around and kind of estimate the pose of those. And what we found was traditional methods like factor graphs that allow for pose estimation could be reused in this context, except you could sort of learn factors that convert the tactile signal into cost functions. And so we continued along that to now incorporate a little bit of local 3D. You could sort of estimate 3D pose of an object as the object is moving around on the sensor, continuing to build on kind of the optimization landscape with some kind of mix of learning, sort of trying to kind of bridge the kind of classical and the kind of data-driven stuff together. Then sort of taking more inspiration from the perception kind of related work in navigation. We sort of looked at LiDAR-based place recognition and sort of reapplied those in this setting to track fingers as they slide across objects. And you can imagine it hitting an edge and sort of collapsing the probability distribution of where the finger is because you've sort of hit almost like a landmark. And then we kind of took those and studied extrinsic kind of perception to enable sort of tactile insertion kind of tasks. So just to summarize kind of all the lessons we learned, it was kind of an interesting way to explore how to translate all the learnings we had from the past few decades in navigation perception research and sort of recontextualize those in the tactile space. So what we found was, at a very high level, it's quite similar. It's essentially a sensor fusion problem, right? You're taking a stream of sensory perception, sensory observation inputs, and you're sort of fusing them and making sense of the world and trying to predict something about the state of the world that is then useful in downstream planning or any decision-making type problems. So what we saw was kind of very interesting parallels, right? As a sort of a finger or a hand is manipulating an object, you can imagine like the locations of fingers through proprioception, sort of similar to a GPS that you would get from like a mobile robot, or a finger sliding on like a kind of descriptive surface, super smooth. If you keep sliding, it's sort of generating shear information, which would give you sort of like a parallel to odometry, right? Like dead reckoning. You're sort of moving the finger along, you're not seeing any features, and so you're sort of increasing your uncertain distribution in terms of where the finger might be relative to the surface. And then as soon as you like hit a landmark, in which in this case, like it could be like a surface geometry or a specific edge or a corner, you immediately collapse the uncertainty in terms of where the finger might be relative to the object. And that sort of relates to like landmarks. And then, taking it all the way at the end, the shape of the object really is like the map of a scene in the context of like mobile robots. But is all the problems solved then? Can we just take everything from, let's say, SLAM and then just apply it to touch perception? So there's some interesting challenges that we discovered, which we sort of compartmentalized into these three buckets. So there's like the problem of locality, which is touch sensors are inherently very local, right? You can kind of touch a very small area in a scene and just get very dense information about that, but the larger scene is kind of not super visible, unlike kind of visual cameras, which can sort of look at something and immediately see a lot of information. And related to that, coverage is also sort of a challenge because you can pan a visual camera once and gather a lot of information over a scene, but for a touch sensor to gather that much information, you'd have to actually slide around fingers for a long time before you even get there. And then the question of like intrusivity, right? Visual cameras are sort of passive. They're looking at the scene without kind of causing any direct effect. But the very act of sensing something through touch sensors changes the world. And it's sort of an interesting interplay between perception and action, kind of visualized here. So we took all of these lessons and sort of really put those together and culminated into kind of the neural fields project, which sort of is the touch incarnation of a full dexterous hand doing essentially slam. The idea is you have a visual RGBD camera, you have your 4 finger touch sensors on an Allegro hand, and it's manipulating an object it's never seen before. And the idea is, can we take all of those live perception inputs in real time and construct a scene, in this case, the shape of the object, and use that shape of the object to track the pose, and it's essentially sort of contextualize this as a SLAM problem. So we solved this through neural fields, where we brought the 3D information from both the visual and the tactile domains into the same sort of landscape, and use that information to train a live neural field. And then that represented the shape of the object to track the pose. One interesting result from this work, and there's a lot more details in the paper I want to highlight here, is sort of like why touch is useful in these settings. And sort of for that, we studied one manipulation run in simulation. And what we did was essentially simulate a whole bunch of cameras around different observation points for the scene as the robot hand is kind of manipulating the object. And what we found was that if you know the shape of the object and you're trying to estimate or keep track of the pose as is getting manipulated, naturally, sort of intuitively, the camera locations that afford more visual observation of the scene, like they're not occluded, give you sort of almost a refinement using touch as on top of vision. So you're sort of slightly improving the tracking accuracy of the object. But as soon as you go to camera locations that are heavily causing occlusions, and you can think of these bottom camera locations, if you just sort of flip the whole scene upside down, it's sort of very natural, right? Like you go grab an object from the table, and naturally your hand is going to occlude your egocentric visual observation, but touch is there to sort of close the gap, at least for humans. And what we see here is that in those settings with heavy occlusion, touch actually helps kind of really make the pose estimation robust. And so this curve is another way to sort of visualize that, where we see from like 0, which is like fully visible object, to 1, kind of no visibility for object. We see that the gap between vision only and vision plus touch keeps widening as the sort of the pose estimation is conducted. So, is the journey over? Have we achieved everything? I think the journey is almost started. There's so much more to do. The work I was describing with neural fields is sort of like in this slow perception regime, where it's taking long horizon sort of perception inputs over time, fusing some information about the world, and giving it enough understanding so you can make longer term decisions, right? Like where to move my finger, how to rotate an object, things like that. But what if you need something that's like much faster, right? Like for reactivity, like if an object slips from my hand, I want to quickly tighten my fingers and kind of grab a hold of it. And for these types of perception inputs or perception systems need to be sort of complemented by something like a fast perception system that's like, taking short bursts of touch information and then immediately regressing to some features that like a reactive policy can use, and kind of quickly make decisions without needing to sort of do long-term processing or kind of build a memory of like what's going on. So that's one of the challenges we were working on over the last year or so. And then, of course, touch is a lot more than geometry, and that's mostly what we've been exploring the last few years. So the question really was, how do we leverage the full gamut of what touch provides, in terms of forces and contact and things like those. So that was kind of another big area we wanted to focus on. And then, of course, why do touch perception in the first place? It's to, make robots have capability in terms of dexterity. So it was like really closing the action perception loop. So with that, I want to kind of use the rest of the talk to essentially describe kind of the details of our recent release across kind of addressing, or at least taking steps in the direction of addressing some of these challenges. So first is the Sparsh, which is a touch encoder, general purpose touch encoder model. So the problem we were trying to address was essentially fast perception, right? How do we get bursts of touch information into some latent information that then can be used for various downstream tasks? And if you've been tracking any of the touch kind of work in the community, you will quickly see that it's quite fragmented, right? There's so many different types of touch sensors. They have like different shapes, different gels, form factors, lighting. You can even see on this slide, like some have dots, and they look quite different. But if you think about like visual cameras, you don't have different models for different cameras, right? It's just one visual model for all the cameras. And so what we wanted to figure out was, can we actually build a touch perception model that works across many touch sensors, and then also it gives you the ability to fine-tune it on various different tasks without needing to kind of design custom models that are only specific to a sensor or a task kind of combination. So what we essentially did here was really abandon the simulation route because of the sim-to-real gaps, and decided to just embrace the real-world data and figure out how to leverage self-supervision, which has made so much progress in computer vision, and apply that or extend those to the touch kind of domain. And we were kind of quite successful at kind of making first steps in that, where we trained a single general purpose model across a large data set, almost 460K tactile images. And what we found was very promising, which is, if you use these pre-trained backbones to do tasks, you can achieve almost, on an average, over 95% improvement on these tasks compared to models that are trained specifically for a task or a sensor combination. This work was led by Carolina and Akash, who are also around, and they're going to be talking about this work in the next kind of poster session. So you can find more details by talking to them. One interesting result I'll highlight here, which gives us kind of a lot of promise in terms of continuing in this direction, is the idea of like few shot transfer. So in this setting, what we did was we took a pre-trained backbone, the Sparsh backbone, and used it to train a decoder for, let's say, a task like textile recognition, and only trained it on a gel side data set. And then what we found was that if you use that same gel side kind of decoder and try it on a digit image, obviously it doesn't work out of the box. But because you have this pre-trained backbone, it only takes 10 samples, which is very small, to improve the kind of task performance accuracy. So you can see from this table, you go from 9% to almost 60% classification success accuracy. Versus if you did not have this pre-trained backbone and you try to do this like 10 shot, it just sort of doesn't make any progress. It still hovers around kind of 10%, which is kind of super low. So that was kind of a very interesting result that we found. This sort of starts taking a step in the sort of slow perception regime. And as I was alluding to, we want this like fast reactivity. We want to kind of go beyond geometry and kind of really embrace the multimodality of touch. So for that, our team had been working on kind of the next generation of touch sensors. This is kind of Digit 360, which culminates in kind of bringing all of those pieces together. So this sensor, you can see kind of in this image how it looks in physical comparison with our older generation Digit kind of version 1. And this is sort of the most advanced sensor in touch today. It gives you, at least in the visual domain, almost human level precision. It has over 18 sensing features, and the spatial resolution is quite mind-boggling. It gives you 7 microns levels of detail, and it can detect forces as small as 1 millinewton. And this work was, again, led by Mike Thingfan and Roberto, who are around, and you can talk to them later more about these sensors. To actually achieve this level of accuracy, Mike and team had to, just sort of design bespoke lenses, right? They were never designed before. It was a super wide-angle lens and a new sort of optical system that would image something at this resolution over like sort of the 360 dome of the finger, so that you can get sort of touch sensing across everywhere you touch on the finger. So the images you see on color in the bottom left are comparing kind of what the images look like from a Digit 360 compared to the older generation Digit. And then, as I was alluding to, touch is inherently multimodal. It's not kind of one thing. Us as humans, we sense a lot of things from our fingers, right? We sense sort of forces and contact and vibration, temperature. So we packed a bunch of other modalities into this sensor as well. So that beyond sort of this like visual image, what you can get from these this sort of full sensor is a bunch of other modalities like IMU, contact microphones, which will give you sort of vibration information. There is a temperature sensor, there is a pressure sensor, there is a smell sensor as well. And together, I think all of those really open up lots of interesting sort of perception problems and planning problems in terms of how to leverage all of these modalities together to do kind of really interesting tasks. Also, we have a on-edge AI accelerator embedded directly in the sensor. So this allows you to actually bake in models directly on the finger without needing to process it on a kind of external computer. And that allows you to actually build super reactive policies that sort of mimic humans' reflex arcs. And this is sort of one example where you can kind of poke on a needle and like it'll quickly react to it. And that's because of the edge AI capability on this sensor. So how are we kind of doing all of this research? So we had our models, we had our sensors, but it had to come together on a hand. So what we were doing was creating this like Digit Plexus platform, which is sort of a standardized hardware software infrastructure that really brings all of these touch sensing modalities together into kind of a common kind of firmware and hardware framework. So you can just essentially plug like a single USB cable and get all the data and all the signals into the same framework. So it works across skin sensors, reskin that we've been using, and then the kind of older generation of Digit, new generation of Digit, and perhaps other tactile sensors. So we've recently open sourced this as well with the hope that the pieces from this either can be just directly applied to Allegro hands that you folks might have, or with even other types of hands, because they give you sort of individual circuit designs and kind of software, firmware for putting the pieces together to build your kind of own tactile sensing hands. And the hope is that this sort of gives the community some sort of standardization in terms of how to build kind of unified platforms. This has powered a lot of work, recent work in our team as well. The neural fields and sparsh work that I talked about was enabled by this Digit Plexus platform, and also some recent in-hand translation work as well. And to really open up access to all of this that I talked about today, of course, all the code, models, data set, all of that is already open source. But there is still a barrier, right? Like if everyone wants to really use and invest in tactile sensing, but how do you get that, right? It sort of requires a very unique expertise in terms of building these sensors and building the hands. So we really wanted to figure out how to lower the barrier to entry for those types of things. And so what we did was we created strategic partnerships with two industry leaders. So the first one, Gelside Inc., which if you're in the tactile space, of course you know about them. We partnered with them again to commercialize the Digit 360 sensor. And so what you can do now is kind of in the next year, go on their website and buy a Digit 360 just off the shelf, ready to go, similar to what you can do with Digit V1s today. And there is also a call for proposals. The link is digitml/CFP, which you can apply to with your research proposals and get even earlier access to use these sensors in your research. The second partnership we struck was with Monic Robotics, which if you're in the dexterity space, of course you know them as well. They're the ones that build the Allegro hands, and they've been kind of at it for decades. And we couldn't have imagined a better partner to figure out how to kind of piece together all the kind of wish list items they had for their hands in their next generation. We had of course, everyone has gripes about frustrations with using Allegro, even though that's really the best platform out there. And so we had a lot of wish list items as well. So we got together and figured out, okay, how do we kind of make those happen, including making touch sort of a first-class citizen in those new hands. And so we struck this deal, and we're kind of co-creating a new platform that will be available for purchase kind of next year, which will be fully integrated with touch. And so, no loose sort of electronics, dangling cables or anything. You just sort of buy the hand. It has all the touch sensors in it already. You just plug a USB-C cable or something and you're ready to go. And there's more information on that website. And if you're interested in keeping track of when it officially gets announced and when it's available for purchase, you can sort of fill up a quick kind of 1-minute interest form on that webpage. So with that, I'll leave you with this interesting video that we recently shot with all of our recent work. And this blog post has all the links to the papers, code, deals, and interest forms and call for papers, all of that. Thank you. I think we can take questions.
Any questions?
Hi, thank you for the great talk. How do you think to extend the tactile perception capability for deformable objects when the interaction actually change the shape of the object?
Yeah, that's a good question. I'm not sure if we need to design kind of new touch sensors that specifically address deformable objects. I think we just need to build better perception models that can handle deformable objects. Does that answer the question?
Yes, sure. Maybe you get some insight about which aspect of the perception algorithm to handle the deformability.
Yeah, I think what I've seen is some explicit stuff like, neural fields and sort of 3D perception methods with point clouds and things like that, and that have gotten us far. But as with kind of most things, I think the answer is somewhere in the middle, where maybe the perception needs to happen in some sort of latent space where you don't really need to think about reconstructing the exact shape or deformations, but mostly care about kind of the right level of detail or feature that's enough for a decision-making system downstream. But of course, that's assuming that what you really care about is manipulation and not necessarily just sort of estimating kind of the perfect state of the object.
Hello, thanks for the talk. You mentioned Metapluxis is open source, right? Yeah, so I was wondering how is it open source? So can anybody from any lab follow the instruction or 3D models of your robot hand to replicate your device?
Yes, exactly. The circuit designs, the 3D printed parts, the CAD models, the firmware for all of those is all kind of open source.
How about the sensor part, the fingertip?
Yeah, the fingertip, the sensor itself is also open sourced. I mean, it's going to require some custom kind of setup to build those lenses and manufacture the gel. But yeah, if you're willing and interested in doing that, definitely try it out.
So is it possible to buy the sensor part from you?
Yes,
directly?
so that's the partnership with GelSight. They're going to be the ones to kind of manufacture and distribute that, similar to the older generation, which was Digit, and we're hoping that's going to be available for purchase next year. But if you want access sooner than that, then you can apply for the call for proposals as well.
Okay, thank you.
Yeah, I had a question about industrial application versus research. So, what do you think are the target force levels for these sensors, and do they drift over time? Let's say if you're using them for 10,000 cycles for a heavy object, or are they better suited for sort of lighter in-hand manipulation?
So I think the vision-based sensors don't have that much hysteresis. Of course, they'll eventually wear out because they're based on soft materials, and they will wear. And then there is a sort of a trade-off between how sensitive you want the sensor, and therefore uses sort of softer, lighter materials. But then obviously they wear out. So there's a sort of a trade-off between those. Does that fully answer your question? I think that there was a second part.
Yes, it's fine.
Okay. Last question here.
Thanks for the talk. You already mentioned that forces is the next step beyond geometry. Did you already look somehow into, for example, dexterous assembling, which is a big field? And do you see more end-to-end solutions there? Or what is your impression from your current state of knowledge?
So for assembly, I think the interesting part that touch plays a role in perhaps is the places where you're directly interacting and trying to fit things together versus sort of the higher level component of assembly, which is more like task planning, right? So I think that's definitely useful, but it's maybe not necessary to study it only in the context of, I guess, assembly, because there's just sort of a general set of tasks that you can sort of study without needing to worry about kind of the high level kind of decision making as well to figure out which parts go. But of course, you can sort of bake that into the system and still study that.
But you have not done deep analysis of, I don't know, fusion processes or inserting the old peg in the hole or something like this? Right?
Yeah, I briefly mentioned this work called neural contact fields, which essentially looks at how you can use touch between your finger and object to estimate what is the contact between the object and the environment. And that usually is a setting where we tested it in insertion tasks. And we found actually that if you explicitly estimate the extrinsic contact, it does improve insertion policies quite a bit compared to just sort of raw inputting tactile sensors and kind of letting the policy figure things out.
Okay, thank you.
Thank you, Mustafa. Thank you for all the questions. I think it's time to move on. Let's thank our speaker again. The next one would be Poster Spotlight.
So hi, everyone. I'm Yunzhu Li, an assistant professor at Columbia University. I will be the chair for these spotlight sessions. So for all the spotlight speakers, please try to line up here on the left side of the stage for your talk. So just to repeat the spotlight instruction, each spotlight video will have 60 seconds and will run automatically one after another. We actually time it. The walking time from the ends to here takes 7 seconds. So if your video already started, please run. And the next 5 presenters, please queue up on the left side of the stage. Order of spotlights is given on the website. So is the speaker for the first spotlight here, generalized animal imitator? Okay.
This is where I'm presenting our work, generalized animal imitator agile locomotion with versatile motion prior. Our method enables robots to learn diverse agile locomotion skills with a single controller, and the learned motion prior can be used for diverse downstream tasks. In these 2 videos, our robot performed different types of jumping, different turning, running, and backflipping with the same low-level controller. The main challenging is to learn different agile locomotion skills at the same time. We train our robot with RL using adversarial style reward and fine-grained tracking reward. Our low-level module takes robot state and latent command to produce low-level skills. We compare our method with different baselines. Our robot can track the base movement of the robot faithfully and produce natural joint movement. Motion imitation baselines tracks the base movement but produce unnatural joint motions, and scale baseline tracks joint motion but fail to learn agile locomotion skills. We also provide original motion in animation for reference. Here's another example of our method in the wild. And also, this one is the visual manipulation with legs. In this project, we developed a system that enabled the quadruped robot to manipulate objects using their legs, inspired by how animals using limbs to do most locomotion and manipulation. Our approach combines a visual manipulation policy with a local manipulation controller. The visual policy trained with reinforcement learning leverage point cloud data to decide how the robot should interact with the object to align with it precisely. And the controller then coordinates the leg movement and the body stabilization using MPC and impedance control. The setup allows the robots to select the optimal legs to push the object towards a distant goal and perform complex tasks like flipping or multi-object manipulation. We test these results in both simulation and real-world environments. While it showed significant improvement over the previous baselines, please feel free to come to our poster if you'd like to discuss this work a little bit more. Thank you.
Hi, I'm Alan from MIT CSAIL, and I'm excited to present our work on learning visual parkour from generated images. So we all know that simulation is a scalable way of collecting data for robots. But although we're able to simulate various terrains and failure cases for our robots, simulations currently lack the visual diversity and realism you might expect from the real world. So in Lucid Sim, we use generative models as a source of diverse and realistic visual data. So for example, this quadruped you're about to see is equipped with a single RGB camera. And even though it hasn't seen the real world before, it's able to learn how to scale tall obstacles like this hurdle. So if you're curious or want to learn more about our work, please come check out our poster. Thank you.
There's a video and then you're up. Audio, please. Silent film.
Hello, I'm Presenter Jinyoung Kim. Please scan the QR code first. Our paper's goal is to revise actions before interaction failures. To prevent failures, we consider 4 types of environmental feedback. First, attribute refers to affordances like clean or dirty. Second, appearances is about visual differences based on angles. Third, presence. Check if the expected object is there. Lastly, object relationship explore how objects interact with each other, like a potato on a plate. It is an example. With our method, the agent considers the object state, interact with the correct one, and revises the plan accordingly. Without our method, the agent just interact only with a high confidence score object. After following each plan, the right side, the task is completed faster and more efficiently. However, the left side, the agent can't meet the goal. Please come visit. Thank you.
In this work, we introduce HintAD, a driving captioning framework for aligned interpretability of autonomous driving. Given intermediate outputs from an autonomous driving model, HintAD can generate natural language that aligns with the holistic perception, prediction, and planning process. How many objects are detected in this frame?
There are 6 cars, 1 bus, and 1 bicycle detected.
Tell the detected position of the yellow bus in front of the ego car.
It's about 36.5 meters away at 12 o'clock direction.
Describe the object.
Yellow bus about 22 meters away in the front of ego car is moving quickly in the driving lane. The car changes lane to the right to overtake the car in front.
Predict the driving command.
Forward and decelerate.
There is a bicycle that is to the front left of me. What is its status?
Without rider.
Top nav underlines a major limitation in existing legged navigation works that primarily focus on avoiding obstacles. We integrates a comprehensive path planner with terrain awareness, obstacle avoidance, and closed-loop proprioception. We demonstrate that Top Nav empowers the robot to select terrains with higher traversability and recover the robot from locomotion failure. We demonstrate the successful implementation and quantitative validations of the Top Nav in extensive hardware experiments, demonstrating the automotive path planning and obstacle avoidance ability. We also demonstrate that the robot can recall previously encountered challenging terrain during the phase of online corrections and plan a waypoint to avoid it.
Hello, hi. Looking for an ideal way to gather data for training autonomous robot policies? OpenTeach is your go-to solution. OpenTeach is your go-to solution. By leveraging VR teleoperation, you can intuitively control robots and collect high-quality demonstration data. The system translates your hand movements into precise robotic actions, allowing you to generate large-scale data sets for imitation learning as well as reinforcement learning. As you can see here, we have set up for multi-fingered hands, mobile manipulators, as well as different robotic arms already integrated into our setup. If you want to learn more about our system for easy data integration, data collection, and sensor integration, come and visit our poster. Thank you.
All right. So yeah, I'm Daniel, presenting on behalf of Howdy, who cannot come because of his visa. So consider a robot on a granular surface with 3 objects that it needs to move to target location. We introduced GRAIN, Granular Robotic Avalanche Interaction, a method which trains a neural network to predict where an object on a granular surface moves as a result of a legged robot excavation. This enables the robot to use avalanche dynamics to relocate objects, as you can see here. Yeah. We show GRAIN on a variety of scenarios with a gantry system and a quadruped robot. Our system allows for indirect manipulation of objects to target location where the object moves on the surface. So we hope this inspires future work in indirect manipulation and legged robots on complex surfaces. Thank you.
T3 is a large tactile framework for tactile representation learning across diverse sensors and tasks. T3, or Transferable Tactile Transformers, is constructed with 3 components: sensor-specific encoders, a shared trunk, and task-specific decoders. T3 uses the shared trunk to capture the shared latent representation between different sensors and tasks. Through numerous experiments, we show that T3 achieved zero-shot transferability to novel sensor-task pairings. Its performance scaled with bigger network sizes, and that T3 can also be used as a tactile encoder for long horizon manipulation tasks. We demonstrate T3's usage as a tactile encoder for manipulation through a few sub-millimeter level insertion tasks. We designed a simple behavior cloning agent using T3 as the encoder for tactile input. The clearance between the pins and the mounting holes is only 0.4 millimeters. A large tactile sensing dataset, the Foundation Tactile Dataset, or FOTA, is developed and will be open sourced upon public release of this work. It contains over 3 million data points aggregated from a couple of the largest existing tactile datasets, and its data comes from 13 different camera-based tactile sensors with 11 disparate tasks.
Hi everyone, my name is Binghao Huang, and I'm excited to share our project 3D VITAC, Learning Fine-Grained Manipulation with Visuotactile Sensing. This collaborative work involves Columbia University, the University of Illinois, and the University of Washington. Humans effortlessly perform everyday tasks by combining visual and tactile sensing. Inspired by this, we've developed a multimodal sensing system that uses a soft gripper equipped with flexible tactile sensors. Our tactile sensor features a 16 by 16 matrix with 0.3 millimeters resolution, making it both thin and adaptable. We integrate visual and tactile data into a unified 3D representation space, enabling our visuotactile policy to effectively grasp fragile objects, even when visual information is obstructed. For instance, our robot can continuously retry until it successfully grasps grapes, whereas baseline systems might fail and proceed to the next task under significant visual occlusion. I invite you to visit our poster session 2 for more details and to discuss any questions you may have. Thank you for your attention.
Hello, I'm presenting Thea, Distilling Diverse Visual Foundation Models for Robot Learning. There are many different implicit and explicit diverse visual tasks robots need to solve in order to accomplish tasks in the real world. These include segmentation, depth prediction, visual question answering, and detection. Motivated by this, we released Thea, a model that distills multiple existing foundation models into a single representation. We can use Thea in policy learning and show that across different tasks, embodiments, and policy learning algorithms, we are able to more efficiently and achieve higher performance. We can also recreate the existing features of the existing foundation models, and we investigate which existing foundation models work best for distillation. Our work is available at our poster. number 12.
Hello everyone, my name is Jan Blumkamp and I'm presenting CoVisNet, a cooperative visual spatial foundation model for multi-robot applications. Multi-robot systems require accurate spatial information for tasks like formation control and cooperative object manipulation. CoVisNet addresses this challenge using only monocular cameras, enabling operation in GPS-denied environments. The model estimates relative positions with associated uncertainties, visualizes ovals even without direct visual overlap. CoVisNet also generates local bird's eye view representations for enhanced spatial awareness. We've evaluated the system in various indoor and outdoor settings, demonstrating effective navigation and coordination in complex environments. We've also tested CoVisNet on different robot embodiments and in various conditions. This versatility suggests applications in a wide range of multi-robot tasks. It even generalizes to outdoor environments. Please visit our poster and learn more about CoVisNet. Thank you for your attention.
Hello everyone, I'm Han Xiao. Today I will present our robot exploration. Imagine a future household robot to prepare the breakfast. It needs the ability to fetch and gather the utensils. Key to its exercise is to explore the environment in advance to avoid disasters when cooking. Here is an overview of our system. Come to learn more in our poster. Yeah. To construct our action condition scene graph, our systems get observations and construct the corresponding memories. We leverage our decision-making module to get our efficient frontier-based exploration. Here, the robot opens drawers and doors to see what's inside and update the scene graph. With our graph, the robot is asked to make the table. It can know the exact position and the list of actions to fetch the object. And if the object is not in the scene, it can identify them and ask for help from humans. Yeah, you will see it. Yeah. Thanks for listening.
We will be presenting today in the poster session with the following title. I think many of us have experience with robots failing at object manipulation, which has negative effects on subsequent tasks. To address this problem, we propose the contrastive lambda web former, which detects failures in subtasks using multi-level aligned multimodal representation, which includes MLLMs-generated narratives. Our method outperformed all baseline methods, including representative MLLMs, such as GPT-4, has promising qualitative results, and proved to be usable in the real world to detect manipulation failure, such as this. If you're interested, please come by poster 15, and we'll be happy to answer any questions you may have. Thank you.
Questions?
Cool, we present Gator, which learns a representation across gates. Imagine you're walking and accelerating into a sprint. This skill blending occurs seamlessly, and we want our robots to reproduce this. To discover this behavior, we learn separate terrain and locomotion representations. We discovered that the locomotion latent space is two-dimensional and disentangled. A signal in the vertical axis increases the robot's swing length, while in the horizontal, it adjusts the swing height. However, gates are encoded into the structure of the latent space, and on request of a gate transition, the space restructures, producing intermediary gates, which are unseen during training. We train a planner in the latent space, which adjusts the robot's swing length and height in response to terrain. This improves the robustness of our system during perceptive locomotion. Please come to our poster for complete details. Thank you. Thank you for watching.
Today I will present our poster, a verification of neural control barrier functions with symbolic derivative bounds propagation. The authors are from the Robotics Institute at Carnegie Mellon University. Neural control barrier functions are used for guaranteeing the safety of the dynamical system by ensuring forward invariance, which is once entered the safe set, it will never go out of it. It has an equivalent condition, which is the derivative of the control barrier function. Contains two parts by chain rule. One is the gradient of the neural CBF. The other is a derivative of the state. And then our focus of the paper is to verify that the learned control barrier functions are valid, which is to verify this term is negative. Please check out our poster for more details.
Hi, everyone. So I work in the asymmetric learning setting for partially observable MDPs, extending from this similar setting for MDPs. So the idea is that we want to leverage the availability of the state during training coming from a simulator, for instance, so that we can better train history-based policies. So compared to previous work that use state as an HR information, and to train a value, to train a state-based value function, we directly use information, mutual information between the history and the state, so that we can directly reward action that gain more information about the state. So for more information, please go to our poster session.
Hi, I'm Abhishek, presenting multi-strategy development and learning and adaptation. We consider long horizon point goal navigation in unfamiliar partially revealed environments where learning is used to inform robot behavior. To perform well in a wide variety of these environments, the robot must improve during deployment via online learning or domain adaptation. However, picking one such strategy in advance risks poor performance during deployment. So our goal is instead we deploy multiple learning strategies in parallel and choose the best performing among them during deployment. Our approach enables the robot to select the best policies quickly, even as they evolve during deployment via online learning or visual domain adaptation. We use bandit-like selection strategy and so preserve guarantees on asymptotic sublinear regret. Find me as the poster session for further discussion. Thank you very much.
We present structure-based meta-learning for data-efficient visual tactile model estimation. We enable data efficiency by learning a prior distribution of visual tactile models from diverse real-world objects. Here we show the robot touching artificial plant. We collect RGBD streams and corresponding tactile data. Given a novel object, we use the prior learned offline to make zero-shot prediction of material parameters from vision alone. Here, for this orange tree example, the branch is predicted to be stiffer than the leaf, as expected. Once the robot begins touching the plant, it uses the tactile data to update the estimation. For example, we can see the leaf region is initially estimated with very low stiffness, but because there are branches behind the leaf, the contact force is higher than expectation. It updates the estimated stiffness to match the observation, as in the red circle region. Our method has sufficient compatibility to learn a prior shared over multiple data categories. Here we show a unified prior learned from data with plants and shoes. For more details, welcome to our poster session.
Hello, everyone. Today I want to share papers about object-centric dexterous manipulations from human motion data. IL usually requires people to hand design the reward, as it is difficulty to exploration in high-dimensional action space. So the pure IL is hard to solve the bimanual dexterous manipulation. We first use imitation learnings to train a generative models on the entire arc data sets whose input is object trajectories and the output is the hand trajectory. After that, we use both hand trajectories and object trajectories as input to train the low-level controller using IL, and output the dexterous hands, fingers, and wrist motions. We can see that our framework can accomplish a lot of very challenging dexterous manipulation tasks including open a book, some articulation manipulation tasks like open a coffee machines, and bimanual coordinations such as lift the laptop and put it down. It should be noted that all videos are played at the original speed. Thank you.
Hi, my name is Kalen Garrett. I'm a research scientist at NVIDIA, and we present SkillGen, an automated demonstration generation system for robot imitation learning. SkillGen takes in as few as 10 human demonstrations and is automatically able to synthesize upwards of 1,000 demonstrations to train policies. SkillGen operates between two phases. First, a motion planning phase that moves in between contact, and then a human demonstration adaptation phase, which warps existing demonstrations with respect to the current poses of objects. This allows SkillGen to be robust to large variation in initial poses and also generate demonstrations in the presence of clutter. We find that policies trained on SkillGen data outperform those of the state-of-the-art by about 50%. Additionally, SkillGen generation is robust to real-world clutter. And finally, these policy improvement takeaways also apply in the real world. Lastly, we find that SkillGen is able to transfer zero shot to the real world with only one human simulated demonstration. Thank you.
Hello, I'm Feng Bo. Our work is deft catch, learning to catch arbitrary objects with dexter hand. Compared with pick and place tasks, throwing and catching behaviors have the potential to increase the speed of transporting objects to their destination. Our work relies on thousands of different objects and can work on generalizable postures. Some postures are difficult to finish a task because of the lack of the support surface. We show some performance of our system. Our system can be generalized to arbitrary postures and diverse objects. Our results demonstrate the algorithm's ability to catch randomly rotating objects in the air, even when dealing with challenging objects like pens. Thanks.
I'll introduce our existing work, Go-Reach in Policy Learning, for non-expert observation about effective sub-Go guidance. We address Go-Reach in Policy Learning by utilizing non-expert action-free observation data. It contains task-relevant information and enables us to extract guidance cues for achieving efficient policy learning. We developed a diffusion strategy-based high-level policy that generates reasonable sub-Goes as waypoints. Additionally, we learn state Go value functions to encourage efficient Go sub-Go reaching. The two components naturally integrate into the OFF policy actor-critic frameworks, enabling efficient Go attainment through the informative exploration. We evaluate our methods on complex robotics navigations and manipulation tasks, demonstrating a significant performance advantages over existing methods. This capability arises from reasonable sub-Goes, thereby clarifying guidance and resulting in informative exploration. Our ablation study further shows that our method is robust to observation data with various corruptions.
Hi everyone, I'm Adam and I'm here to present our work called Avoid Everything. Human spaces tend to be cluttered and dynamic. In order to operate effectively in uncontrolled real-world spaces, robots must be able to navigate safely around obstacles while in proximity to hazards. While traditional methods are very effective at pathfinding, they tend to fail in partially observed settings, such as these scenes observed by a static depth camera. Previous neural methods have stronger performance in end-to-end settings, but they often collide in problems that require proximity to obstacles. Our paper proposes a new neural technique that handles these kinds of tough problems. We introduce two new techniques to learn a collision avoidant policy. First, we introduce a new transformer-based architecture that we use for large-scale pre-training. Second, we introduce an architecture-agnostic fine-tuning technique that uses optimization to correct failures and provide them as examples for fine-tuning. Our method significantly outperforms other techniques for end-to-end reaching. Come check out our poster for more info.
Hi, I'm Max, and we're here to present AnyRotate. So human hands are capable of achieving a range of dexterous skills with the hand in different motion. For a robot hand, harnessing rich tactile information to achieve this level of dexterity still remains a significant challenge. Existing work often reduces the high-resolution tactile data to low-dimensional representations, which opens the question, what can be gained with rich tactile sensing? So in our work, we present a tactile robotic system that is capable of general in-hand object rotation about any rotation axis, and also in any hand direction. The policy can generalize to unseen objects of different shape, size, and mass. And it's also robust enough to be deployed on a rotating hand. We also have a demo on the second floor, so if you're interested, please come and see us. Thank you.
In online imitation learning, Agent improves itself through feedback from expert demonstrations. However, limited expert trajectories struggle with extensive exploration. In this work, we propose key state-guided online imitation learning method. By decomposing the task into what to do and how to do, the agent could conduct task-aware exploration, accelerating online imitation.
Hi, good morning. So for the goal of this work, our idea is to basically train a single policy without any knowledge of the door, just tell it where the door handle is and where the door is, and to have the robot basically just, you tell it go and it should just open the door. So unlike previous methods, we don't need to tell the robot anything about the door dimensions or anything about the way it opens. We use basically a teacher-student distillation to learn the behavior, and then to have the robot basically learn to estimate like properties of the door, such as the opening direction during deployment. So basically the policy basically has an internal belief which you can decode online, which is correlated to the behavior, whether it figures out if it's push or pull. So pulls doesn't work, it tries to push. And we also learned that without training from any like pushes or disturbances during training, this teacher-student distillation can actually learn robust behaviors through external disturbances. And I think, that's it. Sorry, I talk a bit fast. But please check out our poster. It's 29, I think.
Hi, I'm Tarek. This is Finn from the Norwegian University of Science and Technology. So unfortunately, we could not afford Spot, so we built this thing instead. The goal was in-flight attitude control using leg movements, much like the self-righting motions of a falling cat. So here we trained the policy in zero-gravity environments in simulation, and we tested initially on a rotating pole system. So here, what we find particularly cool is that it's robust to the pole constraints, even though it has never seen the pole in simulation. Here it's following a reference set point in the roll configuration. Our main result, however, is demonstration of the policy in free fall. So here, in 0.7 seconds of free fall, we achieve attitude control of 45 degrees in all degrees of freedom. If you want to know how to perform sim-to-real and robust performance on pretty cheap hardware, please chat with us on poster number 30. Thank you.
We present Diffuse Loco, real-time legged locomotion control with diffusion from offline datasets. This sequence of transitions between diverse agile skills, notably bipedal locomotion, is deployed with a single policy trained entirely offline. Offline learning at scale has led to breakthroughs in CV, NLP, and manipulation domains. However, scaling up learning for legged locomotion, especially with a single multi-skill policy, presents significant challenges for prior online RL methods. To address it, we leverage diffusion models to scalably learn from offline multimodal datasets with diverse locomotion skills, accelerated for real-time control. This allows robustness on ground conditions, switching multimodal skills, and much more.
Morning, everyone. We present ClarGen, which is a cluster scene generator for robot learning. Creating a simulation environment from scratch is very hard. Objects can collide with surfaces, fall due to gravity, or even explode when their number increases within a limited area. To fix this, expert engineers need to adjust each object's pose manually, which blocks layout randomization and is super inefficient. ClarGen automates the whole process and can create physically compliant diverse, and cluttered scenes without expert intervention. The most impressive thing is it can directly deploy on various furniture for the scene generation after training. CoRL can also be used to safely rearrange objects to human-preferred setup, generate a synthetic dataset for stable object placement policy training, and then they shall deploy to the real world without any fine-tuning. That's it. Please check out our post during the post session. Thank you.
Hi, I'm Jim from IIT. Our work focuses on enabling humanoid robot to perform complex local manipulation tasks with human-level autonomy. Given a task instruction, the large language model generates a hierarchical task graph that guides the robot motion. The robot learns new skills through reinforcement learning and whole body optimization. It can also choose the best motion morphology depending on the object and the environment. We first do the training, upper body training, and then generate the whole body motion. And then validate in the real world environment. We also create the motion library for our humanoid robots. For more details, please refer to Hypermotion. Thanks.
Hi, I'm Elliot, and I will be presenting Solo Parkour, Constraint Reinforcement Learning for Visual Locomotion from Privileged Experience. We train visual parkour policies for the open hardware Solo 12 robots. These skills require agile yet safe behaviors, pushing locomotion to the robot's physical limits. To achieve this, we frame parkour as a constraint reinforcement learning problem, allowing us to aggressively maximize rewards while maintaining safety. Moreover, parkour requires tight visual-motor coordination. We propose to train the visual policy end-to-end with reinforcement learning, from depth pixels to robot actions, by introducing a very simple, efficient reinforcement learning algorithm relying on privileged experience transfer. If you want to learn more about the method, I will be delighted to see you during the poster session. Thank you very much.
Hello, I'm Deepak. I'm presenting our joint work. The problem statement is to track nominal policy and obey safety constraints and actuation limits. Our problem solution approach is the CVF-QP, which is agnostic to nominal policy. We ask what is the least invasive CVS or best. It is characterized with physics-informed approach with the Hamilton-Jacobi PDE, and we applied physics-informed deep learning. We enforce the safety constraints through our parameterization. We apply intelligent sampling and self-supervised learning to train. Validate on 70 fixed wing bang system. Thank you. Please, I'm happy to chat at poster 35.
Meta control automatic mode-based control synthesis for heterogeneous robot scales. Different scales have distinct requirements. Moving needs spatial awareness to avoid collisions. Opening requires compliant behavior. Wiping requires consistent force. Balancing requires high-frequency feedback. These varied requirements make it difficult to rely on a single control strategy for all tasks. To address this, we introduce Meta Control, a framework for scale synthesis by automating the export process of designing control systems with the help of large language models. Its model-based nature enables complex scale synthesis, robustness to environment variation, cross-embodiment generalizability, and also efficient parameter tuning, and also formal analysis. So if you are interested, please stop by. Poster 36.
Hi, I'm John, and I'm happy to present Dreaming to Assist. The question we want to address is how can we resolve the different intents of a human? And for instance, in a race, a driver might wish to pass or stay behind another car, and use that to train a shared control assistant that helps them achieve their objective more optimally. So To address this, we combine the strengths of world models, intent awareness, and fictitious co-play. Our instances are first that we can train a world model aware of intent, and secondly, that we can leverage the expert's demonstrator's reward to bootstrap our assistant. We then deploy this in a shared control setting, which we interact with the driver via steering and control nudges, actuation nudges. We're able to keep the human safe and able to nudge the human in a way that assists them to achieve their objective more optimally. So also seamless integration with humans in the loop. And please visit us at our posters, number 37. Thanks.
Hi, this is Youngsun Lee from University of Michigan. Inverse source problem is about reconstructing unknown external source functions given partial noisy observations. These problems are common in robotics, such as in manipulation, robotic sensor domains, and more. We solve these inverse source problems by leveraging physics equations and their constraints using neural network solver. In contrast to data-driven approach, we adhere to physics while learning from unpaired data set and is very generalizable. And in contrast to conventional method, we offer flexibility to diverse constraints, robustness to noisy partial observations, gradients, and without the need for discretizations. We showcase various experiments, including 2 real-world cases, membrane sensor, and soft objects contact problem. Thank you.
We propose a novel region-aware grasp framework for efficient 6DOF grasping, consisting of normalized grasp space and regional normalized grasp network. With RGBD images input, graspable patches are extracted through an adaptive grid generator, converted into normalized grasp space, and fed into the regional normalized grasp network to predict regional grasps. RingNet outperforms current state-of-the-art by a large margin on all dataset splits, especially on the unseen splits. Our method also achieves the fastest inference speed, implying the potential to be applied in dynamic scenes. We conduct real-world experiments under 2 settings, cluttered and dynamic. Our method achieves an impressive success rate in clutter removal and performs more consistently under different noise levels. Experiments also confirm that RNet can accomplish dynamic grasping at a satisfactory success rate by executing closed-loop controlling with real-time grasp detection.
Hello, I'm Azon, and we're presenting Aloha Unleashed, a simple recipe for robot dexterity. Imitation learning for dexterous manipulation has come a long way, and we've seen promising results with methods like diffusion policy, as well as intuitive teleop systems like Aloha. Given these results, how far can we push imitation learning for challenging tasks? We show that we could learn dexterous tasks like tying shoes by straightening the laces and tying them into a bow, hanging t-shirts, which involves deformable object manipulation, and replacing a finger on a robot with handovers and precise insertions. We show that we could learn these tasks with scalable data collection, with diffusion policy, and a transformer-based architecture. To know more, see our website and visit our paper. Thanks.
It is desired to equip robots with the capability of interacting with various soft materials as they are ubiquitous in the real world. While physics simulations are one of the predominant methods for data collection and robot training, simulating soft materials presents considerable challenges. It is significantly more costly than simulating rigid objects in terms of simulation speed and storage requirements, restricting the scope of studies on soft materials to small and bounded areas, thereby hindering skills learning in broader spaces. Here, we design a novel spatially adaptive scheme on top of the material point method, which draws inspiration from the octree structure and is capable of adjusting the simulation precision for different spatial regions based on the robot agent's location. Our framework markedly reduces the demand for extensive storage space and computation costs required for large-scale scenarios involving soft materials. We also establish a set of benchmark tasks including manipulation and locomotion tasks to evaluate various RL and trajectory optimization techniques. Thanks.
Good morning. I'm presenting our work Perceived with Confidence, or PWC. In this work, we asked the question, how can we guarantee the reliability of the outputs of learned perception systems in new environments for navigation tasks? We use conformal prediction to calibrate the uncertainty of the perception system and tackle two challenges of generalization to new environments as well as closed-loop distribution shifts. Next, we use this calibrated perception system online in conjunction with a safe planner and a non-deterministic filter. Because the calibrated perception system is guaranteed to be correct, when it is used in conjunction with a safe planner, we ensure end-to-end safety. The system is able to navigate safely around obstacles and provide up to 40% improvements in safety compared to other baselines. Please come check out our poster for more info. Thank you.
Hello, my name is Benjamin Wilson, and today I'll be presenting our work titled What Matters in Range View 3D Object Detection. The range view is the natural format of a LiDAR sensor representing 3D points as a dense 2.5-dimensional image. In this work, we demonstrate that by combining several straightforward techniques, we can create a range view 3D detection model that competes with strong voxel-based methods on the Argoverse 2 dataset, while also setting a new state-of-the-art for range view methods on the Waymo Open dataset. In this video, we show the detections from our best-performing single-frame LiDAR model on the Argoverse 2 validation set. RGB imagery is shown at the top solely for visualization purposes. The bottom portion of the video shows the ground truth cuboids in blue, the true positive detections in green, and the false positive detections in red. Thank you.
We present SPERSH, self-supervised touch representations for vision-based tactile sensing. SPERSH is a family of models for general-purpose touch representations. We trained SPERSH on over 460K tactile images from various vision-based sensors, such as digit and gel sight. SPERSH can be used for downstream tasks, such as force estimation, slip detection, pose estimation, grasp stability, textile recognition, and to train manipulation policies. In this work, we provide a recipe to adapt self-supervised learning objectives from computer vision to the tactile domain. We curate unlabeled data from existing tactile datasets, and we explore the utility of self-supervised learning approaches such as masked autoencoders, Dino, and JEPA. SPERSH outperforms all tasks in our proposed benchmark with a 95.1% improvement over end-to-end approaches. SPERSH is a major breakthrough towards a general pre-trained backbone for vision-based tactile sensors, and our benchmark sets the stage for evaluating future work in tactile representation learning.
Today, I'd like to introduce Shadow, a method for cross-embodiment policy transfer. Robotics hardware is getting increasingly diverse, yet collecting large-scale data sets on every new embodiment is prohibitive. To address this challenge, we propose a simple data editing method that enables zero-shot policy transfer to unseen embodiments. Our method overlays the segmentation mask of the training robot with that of the test robot, for which no data has ever been collected. This aligns the visual representations of different embodiments, enabling robust policy transfer while being extremely data efficient. We test our method extensively in simulation, showing successful transfer across all 4 embodiments that we test. And we also test our method in the real world, where we show high success rates transferring to a different robot and a different gripper. Come check out our poster to learn more.
Hi, this is Chu Ye. In this work, we propose a distributed hierarchical locomotion strategy for multi-agent embodied cooperation. And we demonstrate its potential for scaling up to large number of agents. Yes, and firstly, our hierarchical framework composed of 3 different layers, which enable us to focus on solving the long horizon cooperative task. Yeah, and one of our key contributions is that we use a fully decentralized methods, and we strictly limit each agent observation. This definitely makes our training much more challenging, but at the same time, it makes it theoretically our method could scalable to unlimited number of agents. Yeah. And at the same time, we build different scenarios in the simulator ISAXIM as the benchmark, and we found great emergence of cooperative behavior in these scenarios. For more details, welcome to our poster. Thank you.
Hey everyone, so we present a method to avoid static obstacles with an event camera in the hope of enabling faster, more agile, vision-based robotics. This is the first work that successfully pre-trains an events to control robot policy in simulation and then transfers it to a continuous control in the real world. During this forest flight, the event stream is on the bottom left. We show these results indoor and outdoor at speeds of up to 5 meters a second. A typical vision-to-action learning approach may render a scene and train a policy. However, a continuous time event camera simulation does not exist. To solve this problem, we train an events to action in 2 steps. With simulated expert data, we jointly train events to depth and depth to avoidance networks. And we fine-tune the events to depth perception backbone with real data. This enables real-world deployment. Using this pipeline, we can now avoid obstacles in the dark due to the event camera's high dynamic range. There's more experiments on our website. Come check us out at poster 47. Thank you.
Hello, my name is Yeo Song, and I'll be talking about using genetic algorithms for curriculum design and multi-agent reinforced learning. Now, the cell play has a great potential for discovering competitive behaviors in multi-agent environment, but the cell play also has a tendency to be unstable. So existing approaches so far uses game theoretical constraints and expert demonstrations to stabilize the training, but such approaches can be costly and difficult to converge in a large search space of multi-agent setups. Therefore, we propose using genetic curriculum or a genetic algorithm to help navigate this large search space. And in addition, we remove the need for costly expert supervision by introducing GenOp agents, which are open-loop agents genetically optimized without expert supervision. To validate our idea, we proposed empirical studies and various benchmarks, and we see that our approach performs as state-of-the-art in symmetrical and asymmetrical setups, both competitive and collaborative. Thank you.
Hello, I will introduce our work, EquiGrasp Flow. Humans naturally use the same grasping strategy, no matter how the objects are rotated. This is because we generate grasp poses that align with an object's orientation and position, a property known as SE3 equivariance. However, many existing approaches do not consider SE3 equivariance. To address this, we propose an SE3 equivariant 60OF grasp pose generative model that produces consistent grasp poses for rotated and translated objects. As you can see, EquiGrasp Flow significantly improves grasp success rates when objects are rotated, outperforming current methods. Moreover, our model consistently delivers strong performance across various object orientations. We validated its robustness in real-world grasping tasks involving a diverse range of objects and orientations. Thank you.
Hello, I'm presenting on behalf of Russell Mendoka. In this project, we do model-free RL on a spot robot with an arm to perform mobile manipulation tasks. These tasks are specified by a desired object and configuration of that object, and the challenge in this task is sample efficiency and success. So the way that we achieve this is by 3 approaches. So the first is by baking in some amount of task-relevant autonomy. So we use the autograsp policy on spot for grasping, and we also use a map as a safety constraint, since when we weren't, we broke a window. And then the second important point is we use planning methods as a behavior prior for our policy learning to improve the efficiency of the method. And then the third approach is our reward design, where we use vision language models to be able to get a reward signal for whether or not we're getting task success. So come see poster number 50.
Hi everyone, I am Osan, and today I will be presenting our work on fleet supervised education. In many projects, fleets of robots are deployed to collect data for imitation learning under human supervision or teleoperation. But the question is, how can we efficiently allocate limited supervisors to collect ideal data? These robots operate in diverse states, but only a few human supervisors are available to manage large fleets. And network connectivity can be unreliable. To tackle this, we introduce adaptive submodule allocation policy, which dynamically assigns supervisors based on each robot's informativeness and diversity. It inherently considers network reliability and adapts to changing conditions. In experiments with 100 robots and real-world 5G network data, our method outperforms benchmarks, improving supervision efficiency by up to 3 times. Thank you.
Hello, everyone. We present dynamic 3D Gaussian tracking for graph-based neural dynamics modeling. Using videos captured from robot object interactions, we obtain dense 3D tracking with a dynamic 3D Gaussian splatting framework and train a graph-based neural dynamics model on top of the object particles. This enables action condition 3D video prediction and model-based planning. We demonstrate that our method can find accurate point-level tracking on objects while being robust to deformation and occlusions caused by the robot. For example, given multiple camera views of a rope and a pushing action, our model is able to predict the behavior of the object when the action is performed and render a video. In this example, for a plush toy, you can see how our model predicts its deformation in a visually realistic way. Please stop by our poster for discussion. Thank you.
Hi, my name is Ahmed, and I'm presenting our paper on exploring under constraints with model-based RL and safety filters. So we combine constrained RL methods, which tend to have high constraint violation rates during exploration, with safety filtering methods, which have low constraint violation rates during learning, but tend to have object conflict with unconstraint-based policies. So our goal here is to combine both approaches to learn constraint policies while minimizing constraint violation rates during exploration. So we start with a constraint model-based RL pipeline, and we combine that with a planning-based safety filter that intervenes whenever the base policy is predicted to be likely to violate constraints. We compared our method with different model-free and model-based RL baselines, and we had significantly less constraint violation rate with similar task performance. If you're interested, please come by our poster. Thanks.
Hi everybody, my name is Julian Esser, and I'm very happy to pitch today our recent work on action-based design and reinforcement learning for robot motor skills, which is a joint work by Fraunhofer IML together with MIT and in particular my colleague Gabriel Margulis. We introduce a generalized action space in this paper to express all common action spaces directly on talk level. We do so for a couple of robots, namely the EvoBot robot, the Go-On quadruped, and a couple of robots from the NVIDIA Omniverse Isaac Gym suite. And in particular, we are going to analyze how the choice of action spaces affects different control frequencies and whether action space selection is more about expressive capacities or also about tuning initial exploration for these different action spaces. So if you're interested, we also provide a set of practical guidelines for action space selection in robotics right here at poster 54 at the stairs. Thank you.
All right, so we present embodied chain of thought, an approach for training robot policies to perform grounded textual reasoning. Our method fine-tunes a vision language model into a robot policy that generates textual reasonings followed by actions in response to observations. These reasoning chains consist of both high-level plans and low-level embodied features. In other words, our policy both thinks and looks carefully. For training data, we use a suite of foundation models to generate synthetic reasoning annotations for existing robot demonstration datasets. In our extensive evaluations, we find that our approach outperforms all manner of baselines, especially on challenging out-of-distribution tasks. We also show how it enables natural language corrections of robot behaviors by simply editing policy reasonings. Embodied chain of thought thus presents a simple, scalable, and performant approach for using reasoning for robotics, which we believe to be a promising avenue towards more capable generalist policies. Thank you.
Hi, I'm Noriaki from UC Berkeley and Toyota Motor North America. Today, I'd like to talk about ReLearn, which tries to learn language condition navigation policy from all over the world action-free in the wild videos. So to leverage the in the wild video, we'd like to train nice generalized policy. So now we are using the vision language and robotic foundation model to annotate these videos and train our object navigation policy on annotated data set. And we deploy our trained policy on several kinds of the hardware with different type cameras. So now I'm showing several examples. So our robot with our policy nicely navigates towards the target object condition on the language prompt. Thank you for your attention. Hope to see you in our poster session.
Hi everyone, I'm Eric from the Soft Robotics Lab at ETH Zurich, and today I'll be showing some of our latest work on aerial manipulation. Compared to ground-based robots, aerial manipulators have a unique advantage that they can traverse any terrain, such as floodings, and can therefore be used in scenarios such as disaster relief. Compared to previous works in this area, our system does not rely on external motion capture systems, but rather uses exclusively onboard perception to grasp objects indoors and outdoors. We show an average 85% success rate for zero-shot grasping different objects with different weights, sizes, and surfaces. We open source both our software and our hardware in order to make aerial manipulation more accessible to other researchers. I hope to see you at our poster number 57. Thank you.
Hi everyone, I'm Carlos Ferrazza from UC Berkeley. Today I'm presenting Body Transformer, or BOT, an architecture that biases the vanilla transformer to take into account the structure of the robot body. In practice, we treat the robot body as a graph of sensors and actuators. We then use mask attention to make sure that at every layer of the encoder, a node can only attend to itself and the direct neighbors. We then decode the actions locally at each node. Body Transformer improves imitation learning performance by reaching higher returns, scaling better with model size, and also working well in a low data regime. BOT also improves reinforcement learning performance, and to demonstrate real-time adaptability, we transfer one of these policies in the real world in a sim-to-real fashion. Lastly, attention sparsity also makes this approach potentially much more efficient than the vanilla transformer. Thank you for listening, and I hope to meet you at the poster session.
This concludes the spotlight session number 2. Next will be break and researcher demos from 10:30 to 11. After that, there will be poster sessions. Please note that the papers that were presented yesterday on the first and second oral sessions will also be presenting their posters in the 11 poster sessions. Looking forward to see everyone there.